Hi guys, today I'm telling about you the topic Introduction to Finite Automata. My name is Deepak and I'm here to tell about Introduction to Finite Automata. I'm from EV14. Introduction. Finite automata is the simplest machine to recognize patterns. The finite automata or finite state machine is an abstract machine that has five elements or tuples. It has a set of states and rules for moving from one state to another, but it depends upon the applied input symbol. Basically, it is an abstract model of a digital computer. The following figure shows some essential features of general automation. Next, in a DFA, for each input symbol, one can determine the state to which the machine will move. Hence, it is called deterministic automata as it has a finite number of states. The machine is called deterministic finite machine or deterministic finite automation. DFA refers to deterministic finite automata. Deterministic refers to the uniqueness of the computation. The finite automata are called deterministic finite automata. If the machine is read an input string from one symbol at a time in a DFA, there is only one path for specific input from the current state to the next state. In a DFA does not accept the null move, i.e., the DFA cannot change state with any input character. DFA can contain multiple final states. It is used in lexical analysis in compiler and a DFA is a collection of five tuples same as we described in the definition of DFA. Q is the finite set of states, E is the finite set of input symbols, Q0 is the initial state, F is the final state, sigma is the transition function. Next, we start with the simplest of our machine, the deterministic finite automated DFA. The machine can process an input string shown on a tape from left to right. There is a control unit with states. Behavior defines what to do when the machine sees a given symbol on the current square of the tape. While in a given state, all that have the machine can do is change start begin before going to the next symbol to the right. That is, an acceptor cannot modify the contents of the tape. Deterministic is the context as a particular meaning. When the DFA is in a given state, there is only one thing that it can do for any given input symbol. This is a contrast to a non-deterministic machine that might have some range of options on how to proceed when is a given state with a given symbol. Next, a formalism for defining languages consisting of a finite set of states Q typically, an input alphabet E typically, a transition function delta typically, a start state from Q0 in Q typically, a set of finite state F is equal to Q typically. Example, the set of strings of zeros and ones with no two consecutive ones. L starts from 0 and ends with 1010 and so on. Next, the transition function has two arguments. One is a state and one is an input signal. Sigma q comma a is equal to the state that the DFA goes to when it is in state q and input a is received. Next example, the transition function can be represented as t current state and current input symbol. Next state, for instance, if Q0 is the current state and 0 is the current input symbol, then the transition function is t Q0 comma 0 into Q1. Next, the graph representation of DFS, where nodes is equal to states, arcs represent transition function, arc from one state to state Q labeled by all those input symbols that have transition from P to Q. Arrow labeled start to the start state, new final states indicated by double circles. Next, the example graph of DFS where it accepts all strings without two consecutive ones. Where we can see in this figure, start from A, B, C, where A is the starting point. It is the previous string is okay, but does not end in 1. Where in B, previous string is okay, but ends in a single line 1. In C, consecutive ones have been seen. Next, the alternative representation of a transition table, A where final states are started like A, B, and C, where 0, 1 are the columns and the input symbols, where arrow mark represent arrow for the start states, and A, B, and AC and CC are rows and states. Next, the extended transition function. We described the effect of a string of inputs on a DFA by extending sigma to a state and a string. Induction on length of a string u basics is equal to sigma q comma e is equal to q, and induction sigma q of wa is equal to sigma of q comma w comma a, where w is a string, a is an input symbol. Next, where extended a institution, where convention is the part where w, x, y, x are strings and a, b, c are single symbols, where extended sigma is a computed for state q and inputs a1, a2 by so on by following a path in the transition graph, starting at q and selecting the arcs with labels at a1, a2 and so on an in their turns is called an extended A institution. Next one, the delta hat. In this, delta hat as the extended sigma has had to distinguish it from itself. No needed because they both agree when the string is a single symbol. It is called delta hat. Next one, the language of a DFA. Automata of all kinds define languages. If A is an automation, L of A and its language for a DFA, A comma L of A is a set of strings labeling paths from the start state to final state. Formally, L of A is equal to the set of strings W such that sigma Q0, W is in F. And these are the languages of DFA where example the string in all languages, where we can see the string 101 is in the language of the DFA starting from the A below, where we where we can see from this figure and we can conclude that A is the starting point, B is some in the part of the DFA and C is the ending point, where we can see A is around the 0, A to B at 1 and B to C at 1. C is again rotating at 0, 1 and at B to 0 and A itself has 0. So we can conclude that it has extended string in a language. Next one. So we can say it has a proof of set equivalence. Often we need to prove that the two descriptions of sets are in fact of the same set. Here, one set is the language of this DFA, and the other is the set of strings of zeros and ones with no consecutive ones. Here, we can prove a set of equivalence here. Next one, we have a proof too, where we can see the prove if W is accepted by then W has no consecutive ones. Proof is an induction on length of W. These are the import tricks that can expand the inductive by hypothesis to be more detailed than you need. So we can say, seeing in this picture, A to B starts from starting A to B 1 and B to C it has 1. When C it has 0, 1 itself and B to A 0, 1 itself and where from A itself has 0. So we can say it has the second proof, that is the set equivalence proof. So we have the inductive hypothesis. If sigma A comma W is equal to A, then W has no consecutive ones and does not end in 1. If sigma A comma W is equal to B, then W has no consecutive ones and end in a single line 1. Basics: W is equal to 0, i.e. W is equal to E. Whole, since he has no one at all, holds variously since sigma a comma e is not at B. So in this inductive step, we can assume 1 and 2 are in the state of the DFA. So we can say there are two of the string shorter than W where W is at least at 1. Because W is not empty, we can write W is equal to XA, where is at the last symbol of W and X is the string that precedes. Here, true for X is W is equal to XA. So we can see in the DFA of a figure A to B, B to C, where A itself transfer 1 to B, B to 1 itself transfer 1 to C, and C itself has 0 to 1, and from B itself has 0. So from A it has 0 comma 0 itself. So this is the inductive step. So we can see from itself only. So the next is to it has regular languages. A language L is regular if it is the language accepted by some DFA. Note the DFA must accept only strings in L, not others. Some languages are not regular. Intuitively, regular languages cannot count to attributely high integers. So, as we can see here, the languages that we are seeing does not enshrine the DFA, but it accepted and the strings were in the L. So we can say some languages are accepted, but they are not. So we can say they have high integers and they are regular languages. So thus we can move to the next example, irregular languages. Here W3 and comma YW in 0, comma 1 and W is viewed as a binary integer is divisible by 23. So in this the DFA can take 23 states named 0 from 1 to 22. So the corresponding to the 23 remainders of an integer divided by 23. Start and only final state is 0. So in this DFA of a regular language example, we can see it starts from 23 states, it named from 0. So we can say 1 to 22 are the best ones to take from them. So in this case, the start and final states are end with 0. The next one, example of a non-regular language in this L1, 0 and 1 n by n greater than or equal to 1. So note A is conventional for ICS. Thus 0, 4 is equal to 4 zeros. Example, read the set of strings consisting of n zeros followed n ones such that n is at least 1. Thus L1 is equal to 0, 1, 00, 11, 000, and so on. It accepts of a non-regular language. Next, it is another example where L2 is W by W in the bracket doesn't have anything. So where W is balanced. So we can see the alphabet consisting of parenthesis symbols and like n is the parenthesis symbol. Balanced parents are those that can be appear in an arithmetic expression. Example, these are the examples of no columns with zeros. So we can say here alphabet can consist of parenthesis symbols like and something or something where it does not accepted where W is in the balanced state. So we can say that the balanced parents are those who appear in an arithmetic example expression. So we can see in the example there are only columns but no nothing is in the example of these states. So it's an another example also it can be taken to prove a DFA of a non-regular languages. So these are quietly common to express these that are the expression that can be easily able to be taken by the non-regular languages. So as we see these parents are in the appear in an arithmetic expressions, why these cannot appear in an arithmetic or geometric or linear expressions. So we can see, so these are by another example of non-regular languages. But many languages are regular. Regular languages can be described in many ways. Example, regular expressions. They appear in many contexts and have many useful properties. Example, the strings that represent floating point numbers in your favorite languages is a regular language. Next, the transition of the DFA for L3 means language 3. If string W represent integer I, then assume sigma 0, comma W is I percentage of 23. Then W0 represent integer 2I. So we want sigma of I percentage of 23, comma 0 is equal to 2I of the percentage of 23. Similarly, W1 represent 2I plus 1. So we want sigma I percentage 23, comma 1 is equal to 2I plus 1 sigma percentage of 23. Example, sigma percentage of 15 comma 0 is 30 percentage of 23. So we can see here 2 is great, 2 into I. So 2 into 15 is 33 percentage, 23 is equal to 7. Sigma comma 11 comma 1 is equal to 23 percentage of 23 is 0. So it has another example of language for W by W in 0 comma 1, and W is viewed and the reverse of the binary integer is divisible by 23. Example 0 triple 1 0 1 double 0 is in language for because it reverse double 0 1 0 triple 1 0 is 46 in binary. Hard to construct the DFA, but the theorem says the reverse of a regular languages is also regular. Thank you. Have a nice day. Thank you. Have a nice day.